we need to start building up the computer. So let us do the following. It's time now to wire this whole thing up so that we can actually implement it. Okay? Let's start at the very top. We've seen this before, but it should now make more sense. You are going to start with a computer.vhd. This is the top level. Within it, you will have a CPU block and a memory block. You know that within the memory, you're going to have a program memory, data memory, and ports. That's why coming into the computer, your input ports go directly into the memory system. They need to be wired directly in there because this puppy over here is going to take care of assigning them addresses. This is the address manager over here. Okay? Same thing with the output ports. Output port comes out of the memory system. It's got an address associated with it. It drives it directly to the output ports of the system. Okay? The address only resides within the memory system. And guess what? The CPU also needs to know the memory map. Okay? More so, you as the programmer do. In terms of wires that we need, of course the CPU will produce an address. It comes from the memory address register. It also will provide data going to the memory, data coming back from the memory. We are not going to have a bidirectional bus. On an integrated circuit, you don't do tri-state buffers when you're talking within the chip. You only do tri-state buffers where you share a pin for I/O on the pins of the device. On the integrated circuit fabric, we got plenty of wire. We got plenty of transistors. We don't need to do bidirectional stuff. We do everything unidirectional. Plenty of copper for everybody. Okay? We have one control signal, one and only one, and that is the write. Okay? We are either reading from the memory system or writing to the memory system. Nothing else. Okay? More advanced computers probably have some more stuff, but that's not us. Okay? How's that feel? We've seen this before, but now it's getting real. Okay? You know what we need to do? We need to now define the memory system. And this is where we start. Okay? Within the memory system, we have three things. Okay? We have the ROM, or the program memory, which is a ROM. We have the data memory, which is read-write. We have input ports, and we have output ports. Okay? The trick of all of this is that you have to manage where everything is being routed to. So, for example, you will provide an address to the memory system of where you're going to read or write. So this address will come in, and you know who needs to see it? Absolutely the program memory. Absolutely the data memory, and absolutely the output ports, and absolutely the input ports. Let's talk about the input ports in just a second. When we pull the data out of the memory system, this guy right here, this data out, okay, it can come from multiple things. It could come from, number one, the data coming out of the ROM, our program memory. This will be an opcode. Okay? The opcode comes out of here, or the operand, and it needs to come back, and maybe it's the data out. If we write to data memory, we might put it right here, or excuse me, if we read from data memory, we might get information from here. Where else could we get information from? The input ports. And guess what? There's 16 of them. So you're going to have 16 input ports, and they all need to potentially get driven into the data out port. The way that you handle all signal routing, cross-pointing, everything is with multiplexers. Okay? They're one direction. You have an in, you have an out. But the inputs can be a whole bunch of different inputs that you route to a single output. Who is going to tell which one of these to route to data out? Who knows which of these three things, this, or this, that should be routed to the data output? The address. So you need to design a multiplexer right here that is a big old multiplexer, but it is going to handle routing whatever piece of information in the memory system that the address calls for out to the data output. Okay? So you're going to multiplex and say stuff like this. If The address is within 02. Does anybody remember what it is? 02. Now you're like, holy crap. I need to go pull a number when I'm writing my VHDL code. How do I do that? You do it by this. You look at your memory map. This is a design thing. So now you're coding directly off of the memory map that we've created. So you say, if the address is either between 00 to 7F, go ahead and drive the program memory out to data out. If the memory is within 80 to DF, go ahead and route the read-write memory to data out. Or if it's F0, go grab port in 00, drive it in. Or if it's F1, drive port in 01, etc., etc. So your multiplexer is going to select between the program memory, the data memory, or 16 input ports. There will be 18 inputs into the multiplexer. All 18 of them are 8 bits wide. How the hell are you going to handle that many signals? You write VHDL and everything is a bus. Okay? Everything is a vector. All right, all right. This feels pretty good. This feels pretty good. Does it feel good or is that scary? It's a little scary. Okay. Let's jump into the program memory. Okay? Let's go inside of that guy because that's where it all begins. If I want to write a program, I need to go put bits at address 0, 01, 02. I need to put instruction codes, opcodes and operands in there to do something. We already have a few instructions that we know how to do, but we need to figure out how to get those ones and zeros into the program memory. Okay? You are going to go in to a program memory and you're going to create entity ROM 128 by 8 sync. Okay? You're going to set up the entity to have an address, a clock, and a data out. You know what the first thing you're going to do within your program memory? You are going to set up a table of constants which represent the opcodes that we have decided to use in this computer. Okay? The constant names are going to be the mnemonic names that we have decided upon. Okay? The reason we do that is because if you don't do constants, then what happens is you're programming the computer in ones and zeros. You are literally saying, load A with immediate addressing, and you're going to type hex 86. That is hard to remember. You know what's easy to remember? If I said, I'm going to make a constant, which is called load A immediate, and I'm going to set its value to 86, when I go to populate my ROM array, I can use that mnemonic. Beautiful. Do I use constants for the addresses? You don't. What you use for the addresses that you're accessing in your program is the memory map. You're going to look at this and go, okay, I'm going to set up a variable at that address and I'll call it whatever, var1, and it's 80. Okay? I'm just going to read and write to that thing. I know that I got a port here at E0. I got a port at F1. I got all this stuff hooked up. You have to know the addresses based upon this memory map. Okay? All right. So I'm going to set up this massive table in my ROM. Okay? All right, it feels all right. It feels okay. Now, oh, by the way, where did you get all those opcodes? In this book. Let us go in deeper. Now we're in the architecture. And I want to create the ROM. Okay? It's a ROM. That means you only read from it, which is program memory. That's what you want. Consider the following. I go and set up the following ROM array. It is going to be, I do my whole thing like I did in my homework. I create a new type, which is ROM array. Yeah, let's see. Just like that. Okay? Hang on. I'll get the car sick on me. I say new type, ROM array. It happens to be 0 to 127. How did I know those numbers? That's what the address range is. Those are the addresses, the hard-coded addresses. You're hard-coding these now. 0 to 127, this is your program memory. It is going to be 8 bits wide because we have an 8-bit microcomputer. And now all I need to do is I need to start inserting into my array information. So I come down here and I write my first program. Constant, call it ROM. It's of type ROM type. And for each of the addresses in there, I am going to insert opcodes and operands. Check out what this program does. Load A with immediate. I use my mnemonic. That's just going to substitute 86 into that value. Then at address 1, I put AA. So I've put AA into A. That was fun. And then I stored it to E0. What, do anybody remember what E0 was? That was an output port. And then what did I do? I did a branch always back to 0, 0, and I will execute that loop forever. I have just written a program that should execute forever. Okay? Now it's stupid because it's just you're going to hit reset and it'll go AA and then it'll sit there forever, loop. Okay? What do we do with all the other locations in memory? We have 128 bytes of program memory and we have to tell them to be something. How do you handle it? You might notice this little puppy. Just put zeros in all the other ones. Okay? This is how you write your program in assembly. This is essentially assembly. It's even lower level than assembly, but you are using mnemonics. Okay? This is how you're going to get your computer running for the first time. Just these very simple loops. Okay? Your control state machine is going to have these opcodes hard-coded in the control unit, within the CPU, within this puppy right here. Okay? If you look at the CPU, it's going to have this finite state machine, and it's going to be sitting there banging away, and it's going to grab the opcode and say, oh, it's 86. That means go down this path. So this is now, we're hard coding this in here. We're building the hardware. Okay? There's no more of this kind of, well, it could be this, could be that. It's no, you're coding this directly into your VHDL. Okay? That means, though, you also have to have these constants for your opcodes, not only in your program memory, but also in your finite state machine unit, your control unit. Okay? All right, there is a little trick with the memory system which you only run into once you start simulating. This memory is going to actually see addresses that are outside of 0 to 127. Okay? Because sometimes they're going to be output ports, input ports, or data memory. So this program ROM will actually freak out if you try to read from like 128 or 130. It's going to freak out. So what you have to do is you have to put in a process which handles only enabling the ROM when you're in a valid range. Okay? So here is a way to do it. Okay? This is within the ROM. Okay? You are actually within this ROM right now. You are going to put a process which will look at the address, and you are going to create a local signal which is called enable. And if the address is within the proper range for the ROM, you'll go ahead and enable it. If it's not, disable it. That process then is used by the other process in ROM, which goes into your ROM array, grabs the information, and puts it to the output. So look at this thing. Process. It is only dependent on clock. There's no reset because it's a memory array. It is going to say, if I have a clock, then if I'm enabled, meaning that the address is valid, I will then go into my ROM array, take the address, obviously do the typecasting stuff we've been doing, grab the information, and drive it to data out. Boom. So now what we have is we have this dude designed. You should be able to design that today. Put your first program in there. Life is good. Let's take a look at the read-write memory. You want to do that? Let's take a look at it. Why not? How do I do read-write memory? It's exactly like your homework. You go into this and you define a new type called read-write, and it's an array. But you know what's cool about the array? This is where we hard code the address values. If we look at the memory map, We know that our data memory needs to be between 80 to DF. Okay? That's in hex. In decimal, that is 128 to 223. We have now hard-coded this array, this new type, to only respond to those addresses. We have hard-coded in the memory map. Check this out. It's obviously going to be 8 bits wide. Now remember, this is read-write. So it's no longer a constant, it's a signal, because we need to put stuff in it and get stuff from it. So we do signal of this type we created, read-write. Now, we are now ready to look at how you implement it. Okay? You still need that enable, because this array is going to be seeing addresses that aren't within its valid range. So you're going to go ahead and make an enable process. I'm not telling you how to live your life, but you could copy and paste this from the thing we just did 5 minutes ago. The only changes are going to be the valid addresses. This allows the read-write memory to see those other addresses but only respond to ones that are valid. Then it's simple to create the actual process. Process, clock. There's no reset, it's memory. If I get a rising edge of a clock, and then if it's enabled, now you can either do the write situation, or you can do the read situation. Exactly like your homework, where you're accessing that array, you're either reading or writing, you just have to account for this enable, which means the address that you see is a legal address. How's that feel? Okay. If you did happen to purchase the book, I'm not here to make money, okay, but if you did buy the book, okay, you might notice that there is a considerable amount of VHDL provided for you, okay? And that is by design, okay? Because if I just describe it at cartoon level, you get destroyed when you go to try to code it. So it's very scaffolded. There's parts that you have to do, but I get you to the point where it's like, okay, you're not going to hang yourself because you don't have enough of the actual details in here, okay? How do we handle the output ports? Each output port has to respond to a address, okay? And these output ports are where, okay? These output ports are down here at address E0 to EF. You are going to have a process for each output port that will take the input into the memory system, if it's at an address, and latch it. And once it's there, it holds it forever. And that's beautiful, because when you write to a port, you don't want the port to have that data vanish as soon as you go away. You want it to hold it for all time. If you write AA to the LEDs, you want to go execute other instructions without having those go away. Okay? So check out this. Here's an example of a port that resides at E0. Okay? So I come along to you and I say process clock reset. Reset's back. Why is reset back? This is a register now. This is an 8-bit register, so it has to have a reset. It's D flip-flops. All you do is you check the reset condition, just like normal, and then you say, if I get a clock, then nested under that, you check whether the address is valid and you have a write, and if so, go ahead and take the data coming into the memory system, latch it onto that output port. Okay? That handled our first output port. Then you do another. Then you do another. Then you do another. How many are you going to do? 16. Okay? We'll wrap it up like this. You look at this thing right here. Okay? You should be able to encode your entire memory system. The memory system is a beast. It's a lot of things. It's a big part of this. You're going to have your memory system. You can do the ROM. Put your program in there. You can do the read-write. Hard code the addresses. You can do all 16 output ports. Copy and paste. This right here is nothing more than a multiplexer, which you should be able to do. Okay, the input ports are not latched. They're just read and read by the CPU. So let's recap what we have looked at. We have defined a computer as this thing that only accesses the outside world with ports. Okay, you give it a clock, you give it a reset. It's got input ports and output ports. Okay. The way you tell the computer what it's going to do is with a program that is executed by the CPU. And that sits within a memory system. Okay? What we have is two components, the memory system and the CPU. And we have looked at the memory system in detail. But what comes into the memory system is nothing more than an address and a control signal. And what you do is you read out your program instruction by instruction. You can read and write from what we call program memory, and you can read and write from these ports. They are all assigned an address per your memory map. Okay? All right. So last time we looked at the actual implementation of the memory system, and we dug way into it. What we did is we said, okay, look, you're going to build this memory system, and it has to have a component, which is your program memory. And this we know how to do. Okay, so we looked at the code on how to do this. We set this up as nothing more than an array of constants, and we insert the opcodes and operands in order to implement our instructions. Okay, we had to code this up per our memory map, so we had instructions that went from address 0 to 127. Okay, and then what we did is we created the read-write memory, which was where we have our data memory. Okay, and those were from address 128 to, does anybody remember what it is? Something like 223. Okay, and this was an array of signals, and you could read and write from it. Both of these were directly out of your homework. Okay, but then we ran into the situation where if you're going to be reading from both of these memories, okay, at different addresses, there's situations where the data that comes out of the memory system, you have to figure out which data is going to come out. Okay? So we decided to implement this signal routing multiplexer in order to selectively choose what information is coming out of the memory. Okay? And when we do that, not only can we choose between the ROM, which is a certain range of addresses, the RAM, which is a certain range of addresses, we can also choose from input ports, which are implemented as nothing more than wires from the outside world that are associated with an address. Okay? So using this multiplexer is how we use the address line in order to choose what comes out of the memory system. Okay? When we write, we can either write to the program or the data memory, and we have to give it a control signal, and we can put information in here, but we can only put it at these addresses. We can also put information at all of these output ports. And these output ports were processes. But the process also included an address, a specific address. Okay? So you bundled all this up, and bada bing, there it was.